Yes, dear friends, we are going to start a new topic. AC circuits containing only a capacitor. We know that when alternating currents is applied in a capacitor, the capacitor got continuously charged and continuously discharged. So we have to find out a phase relationship between the current produced and the voltage which applied through the capacitor. Let us start. So we have a capacitors having capacitance C. This is the applied voltage at some times at a particular strength. Let us suppose the total voltage applied in the AC circuit is E naught sin omega t. We know that that voltage at that times will also be across the capacitor. So therefore E is equal to V. We know that at some time if a charge got the capacitor by Q, we know that Q is equal to CV. From here we can calculate the value of V, which is Q divided by C. If I put the value in this format and put the value of V, it will be E naught sin omega t is equal to Q upon C. From here, after simplification, we will have the value C epsilon naught sin omega t. We know that the current rate of charge dq upon dt. If I differentiate this equation number first, I will got a current which will be C A naught omega. Differentiation of sin omega t will be cos omega t. Therefore, it has the value this one. And also, we know that the maximum value of cos omega t will be plus 1. If I place plus 1 for cos omega t, we will get a maximum amplitude of the current which is I naught. Therefore, C times E naught omega. If I write this in this format, E naught omega C and also E naught divided by 1 upon omega C. If I compare this value with current is equal to, we know that current is equal to voltage divided by resistance. If I compare this value, I will have E naught is the voltage, maximum amplitude of the voltage divided by resistance 1 upon omega C. This resistance 1 upon omega C can be represented as Xc. Xc known as capacitive reactance. This Xc whose value is 1 upon omega C known as capacitive reactance. Capacitive reactance. As the resistance always opposes the flow of the current, या change of the current, likely this Xc capacitive reactance also opposes the change of current in this AC circuits. As already discussed, omega C E naught has the value I naught cos omega t. If we have to compare this with this equation first, applied voltage across the AC circuits, we have the same value here sin omega t. This cos omega t should also be the sin omega t. Therefore, using the trigonometrical identity, we know that sin 90 plus omega t will be cos omega t. If I replace cos omega t with these values, I will have sin omega t plus 90. This will be our equation number 2. Now in this way, we can compare equation first and second. So here I naught is current amplitude whose values comes out E naught divided by XC. XC is the capacitive reactance and whose value is 1 upon omega C, and we also know that omega is equal to 2 pi f multiplied C. So our current in the circuit is at the time of t is I naught sin omega t plus 90, and our voltage at that time is equal to E is equal to E naught sin omega t. In this way we can say that our current is ahead of the voltage by n angles of pi by 2, or we can say that the voltage across the capacitor or across the AC circuits is lagging behind the current by n angles of pi by 2. So in this way the phase relationship between current and voltage will be these two equations. Our next part of this derivation is graph between E and I versus omega t. We already found out current has the value I naught sin omega t plus pi by 2. How to draw the graph between I and omega t? This is the current, and this is the graph of voltage. The graph of EMF and omega t, and dotted lines will be the graph between I and omega t. We already know that current is ahead of the voltage by an angle of pi by 2. It means that current will cross the positive x-axis earlier than that of the voltage by an angle of 90 degree. That's why the difference between this should be pi by 2, and it will be pi, it will be 3 pi by 2, and it has the value 2 pi. Also we know that omega, angular velocity, is equal to theta divided by t. From here theta angles turns is equal to omega into t. So it means that this is the graph E and I versus theta, which will be omega t. So here we can say that the difference between the phase angles between EMF and the current at a particular times will be pi by 2. This is the difference of these ones. Okay, it means that whenever current becomes maximums earlier than the voltage become maximum by an angles of pi by 2. So that is the meaning of, that is the difference of phase angles between them. Now we are showing how a capacitors block a DC current and allow a AC current. We already know that the resistance offered by the capacitor is Xc, will have the value omega C. Here omega is angular frequency whose value is 2 pi f into C. So for a DC circuit, for a DC means direct current, DC means direct current, there is no frequency of the current, therefore the resistance offered by the capacitive will be 1 upon 0 will be infinite. So it means that for a DC circuit, the capacitors block the DC current. It does not mean that there is no flow of the DC current. The DC current, if I replace this one, If I replace this value, okay, the DC allowed this is our DC circuits and this is a capacitance C. Whenever you apply this one, when the capacitor is fully charged, till this the current would flow. After charging fully, the capacitors block the current which passing through the DC circuit. That's why after fully charging, we can say that DC block the current flowing in the circuit. But in case of the AC, there is no such type of conditions. We already know that AC has a frequency. For an AC, for an alternating circuit has the frequency 50 Hz. So in this case, it offers a capacitive reactance whose value is 2 pi into 50 multiplied capacitance of the capacitor. So a capacitors allow a AC current easily because in first half cycles, so you know that this is a current, it is sinusoidal. It is sinusoidal. It is like this one. So it is varying magnitude and directions. In first half, the capacitor goes charged. In second half, the capacitor becomes discharged. It means that in first half cycles, AC is given to the charges. Yeah, AC has given some energy to the capacitors in the form of the electrical energy. In second half, the capacitor when discharged and the charge goes to the source. It means that the energy which is already existed inside of the capacitor in the form of the electrical energy is going to the source. Here source is the alternating voltage. In second half, that's why minus means the charge returns back to the alternating circuit. So in this way, in a complete cycles, there is no charge stored in the capacitor. There is no energy dissipated across the capacitor, or I can say that in this AC circuit containing only a capacitor. Next, we will draw a graph between capacitive reactance and frequency. We already know that XC, capacitive reactance, is equal to 1 upon 2 pi F into C. So here I can say that 1 upon 2 pi C is constant. Therefore, your XC is directly proportional to 1 by frequency. So whenever frequency is increasing, if I represent frequency along x-axis and capacitive reactance along y-axis, I have this graph. It means that whenever frequency is increasing, your capacitive reactions go on decreasing. Now, how a RMS values of current related to the RMS value of voltage? We know that IRMS, root mean square current, is equal to I naught divided by root 2. And we also know that I naught is equal to E naught divided by XL. And also root mean square voltage is equal to E naught divided by root 2. From here, RMS value of current is equal to RMS value of the voltage divided by XL, and replace the XL by 1 upon omega C. So if I calculate this one, it will become omega C RMS value of voltage. Therefore, RMS value means root mean square current. And similarly, ERMS we can represent again like this also. It will be root mean square voltage. These are on an average a DC current, DC equivalent to the DC current and equivalent to the DC voltage.